privilege in inviting you all to the second day national level series, Igniting Young Minds Towards Mathematical Research. We have amidst us Dr. Subhash Martha, Associate Dean Student Affairs, IIT Ropar, to share his expertise in motivating the budding mathematicians of Gen Z. Martin Luther rightly said, prayer is not overcoming God's reluctance, but laying hold of his willingness. Let us begin this wonderful evening by invoking the blessings of Lord Almighty. May I invite Mrs. Saujanya, Assistant Professor, Department of Mathematics, to lead us into prayer.
Thank you, ma'am. The scripture portion for this evening is taken from James chapter 3, verses 13 to 15. Are there any one of you who are wise and understanding? You ought to prove it by your good life, by your good deeds performed with humility and wisdom. The wisdom from above is pure of all. It is also peaceful, gentle, and friendly. It is full of compassion and produces a harvest of good deeds. It is free from prejudice. And goodness is the harvest that is produced from the seeds the peacemakers plant in peace. This is the word of the Lord. Thanks be to God.
Thank you, Saujanya. We invite you, sir, with virtual floral greetings. Kindly accept. It gives me immense pleasure in introducing our eminent speaker for today, Dr. Subhash Martha, Associate Dean Student Affairs, IIT Ropar. Dr. Subhash Martha received his PhD in mathematics from Indian Institute of Technology, Guwahati, in 2007. He then spent 3 years at Indian Institute of Science, Bangalore, as National Board of Higher Mathematics postdoctoral fellow. Currently, he is working as an associate professor in mathematics and associate dean student affairs at IIT Ropar. He works in applied mathematics, and his current research interests are focused on the theoretical description and mathematical modeling of water wave scattering by batteries and bottom topography, hydrodynamic loading, fluid flow through porous medium, linear and nonlinear flow in multi-layer channels. Alongside the main theme, he also works on numerical solution of Fredholm integral equations. Main working methods are mathematical modeling, analytical method, and numerical simulation. Sir has published 57 research papers, which includes 5 book chapters, 12 conference proceedings, and 40 journal papers. 4 students are already awarded PhD under his guidance, and 5 more are working under him. He also has guided 7 MSc students for their project dissertation. He mentored 2 postdoc students under DST and PDF, who are now working in reputed institutes. Also, he has guided many summer interns of other institutions. Sir was awarded sponsored research projects from DST as well as from IIT Ropar. He was nominated as member of the National Academy of Sciences, India in May 2022. He was awarded Professor Ghanshyam Shamal Best Presentation Award in the 36th Annual Conference of the Odisha Mathematical Society in 2009 and postdoctoral fellowship by the National Board of Higher Mathematics, India in 2007. He has delivered more than 36 invited talks in different conferences and institution seminar series. He is reviewer of more than 20 international journals. He has been reviewed 8 PhD theses of other institutions and universities. Sir has also worked as an external expert in many outreach activities. To name a few, Sir was jury member in the Young Scientist Conference of the 6th India International Science Festival 2020, external expert for the PhD Viva Voce examinations, etc. Sir has visited many universities, including ETH Zurich, Switzerland, Shanghai University, University of Melbourne, etc. He is a member of other societal societies, such as annual member of the American Physical Society during 2012-13, life member of the Indian Mathematical Society, etc. He's taken many important responsibilities, such as head of the Department of Mathematics during 2016 to 2019, Chairman Council of Warden during 2019 to 2021, and now he is serving as Associate Dean Student Affairs at IIT Ropar from June 2021. With such exemplary and vibrant profile, we are indeed honored to have you with us today, sir. May I have the privilege of inviting you to kindly take over the session.
Thank you, Professor Santoshi ma'am, for this nice introduction. And I thanks you as well as Professor Nirmala ma'am, for inviting me to this platform. And in fact, Hyderabad is a good place. I have been many times to there, and it could have been more suitable if it is in a physical mode. But however, these days, online platform also is okay, where the students and others can enjoy the talks by listening as well as by interacting. Okay, so let me share my
Thank you, sir.
uh, screen then. Yeah, anything else? Ah, okay, so let me share my screen. I think slide is not yet visible, right? I am so busy actually. Actually, I thought that I'll deliver at my home, but I am sorry. So I am still in office. I can screen here itself. Just a minute. Okay. So let it be full screen. Oh my God. Is it visible, ma'am?
Yes, yes, sir. It's visible.
Just I'll go to it is okay. The title looks perfect as you told, right?
Yes, yes.
Okay, so dear students and the faculty members of this St.Ann Women's College, I think all students are your girl students, right?
Yes, sir.
Okay, so I am happy that this is another. I think in Punjab there is a girls' college also. There are, I think, many girls' college, and in fact, in Fatehgarh Sahib or somewhere else, I went in 2017, where more than 5,000 girls are there, and in that conference, I gave a talk. Okay, so it is my privilege to give you to a talk where you'll be motivated to do some work, or you'll be motivated to do research in future related to differential equations and numerical methods. That's what the you want to listen more on applications. That's what I will highlight today. On my research interest already ma'am has highlighted. So I work on modeling on water wave phenomena, and in particular wave structure interaction and integral equations. Okay, so today the outline of the talk is I will start with the modeling on the simple COVID-19 problems, which started in around March 2020 when the lockdown started. The simple model how the people send through WhatsApp, which I just solved it and I put it for interesting only, nothing more for curiosity. And then the differential equation, which has a vital role in the mathematical modeling, I will discuss on related to surface waves and application, where we'll see the differential equation in terms of van der Waals problems and what is the suitable mathematical techniques we can apply. So that surface wave application, I will talk through wave scattering by vertical barrier if time permits. Okay. And when you talk to modeling, you look more on mathematical modeling. And then when you start to model, you get equations, right? How you get equations? And then when all principles and you relate through mathematical equation, then that became mathematical equations. And if there are rate of change, then the rate of change gives the differential equation. And of course, we have always different conditions which are named as initial conditions and the boundary conditions, right? And when you talk, you always tell that whether the problem is linear or the non-linear. I'm sorry. And when you talk about linear and non-linear, you discuss what is the methods is suitable for that kind of problem, whether it is analytical or numerical method. Let us start with the COVID-19 kernel model, or we call that transmission of COVID-19 model, right? I think this is the picture you might have seen. Nowadays, sometimes social medias are showing this, the coronavirus. And what actually I got in WhatsApp when the initial lockdown started, right, in March. Why it is called 19? Because, of course, it from the China, it started in December or November 2019, but in India, we observed it in February end or March, mid-March in India. Okay, so the problem was the following. So on March 1st, 2020, in Kerala, it started actually in Kerala because the Kerala, I think maximum people are going always, or more the flight came to there in that time, and then people are infected. And then somebody sent in WhatsApp, now in Kerala, the number of affected people is 3 in March 1st. And then he was telling that on March 23rd, because the lockdown started March 23rd, the number of affected people was 96 by the coronavirus in between these 23 days. So this is some numbers only. Either I don't know the exact, but it was that time it was there. And what will the number affected people after 30 days if you do not take mask? Because some after that it came masks, use masks and medicine, social distance, etc. That time is nothing. It became 96, right? So you want to now model these 3 statements, what is there in terms of mathematical equations. Now that's what we will formulate it as an initial value problem. Let yt denote the affected people at any time t. Like what is the law? The law is the rate of growth at any time. So the growth means here the infection. The increasing of infection at any time t is proportional to the population present at that time. And so that the equation which you always tell for the rate of growth is dy dt is equal to ky. Always k is positive influence. If you want increasing, if you want decreasing, then it is minus k. But here the infection is increasing. That's what we told it, k is positive. Now it's a simple differential equation, and if you make it the solution, just you integrate it, you'll get c to the power kt, where c is a integration constant. It's very simple. The equation A1 is very simple. And then what is the condition? The condition was on March 0 on 2020, the number of infected was 3. That means when t equal to 0, y equal to 3, right? So t equal to, when t equal to 0, y equal to 3. That means y of 0 is equal to 3. So if you substitute there, we get c equal to 3. Hence y is equal to 3 to the power kt. Very simple. And then the next was on March 23, the infected people was 96. So at y of 23 is 96. So again, you substitute there, and what you get? You get 23k is equal to log 32, where k is this. So your solution was yt is equal to 3 to the power kt, or 3 to the this. Now you tell that after 10 days, that means when t is equal to, because up to 23 you have taken. Now after 10 days, when you take it, is t is equal to 33, we get y equal to 433 people. And now again, after next 30 days, if you don't use mask and this, and then when t is equal to 53, we get, just you put here is t is equal to 53, you get 8,818 people. So this simple, the WhatsApp high actually, which was propagating from throughout the India, people didn't bother about that. Really, this much, this many will be infected really, and afterwards really it infected, and then government started to for lockdown, use coronavirus, social use masks and then social distance, etc. Now you can see that if you do not use in Kerala itself, it has an 8 and afterwards it went. So what you have seen that gave an alarm to stop COVID-19 or coronavirus, which was a simple linear. If you have seen that, this was a linear problem, linear differential equation with initial condition, very simple, right? And it was linear, it was simple to just, it was separable form, you integrated out and got it, right? Everybody can do that. Now you yourself can make a linear problem and solve it, but now the current one is not linear, right? So if you want to take it is total population, which is n, which is s plus I plus r, then number of s is number of individual at time t which can get infected. At the same time, if you tell the number of individual time who are already transmitting, and then some other people are also recovering, and some are also dying that time during this COVID situation, and that is called SIR model. Students who are interested, I didn't give you the detail, but you can put it lot of um, articles which are available in Google also. Some people they didn't publish, but just put it in curiosity. So you will get a system of different, instead of one equation, you will get system of nonlinear differential equation related to this. And when you get system of nonlinear differential with some system of initial conditions, you can solve again the same way. But when it become nonlinear, this nonlinear system, and due to this all the things, the nonlinear system, you may not solve by classical way, but you can solve it by Rangikuta method. Those who have already learned numerical analysis by RK method or the Euler method can solve such problem directly and then plot the graphs. Okay, so I will leave it to. So why these problems COVID virus that time important? I didn't keep more because I have not done anything, just for curiosity for you people. I just extracted further, and there particularly what they talked about this dynamic of this system SR model, which is called dynamical system. Some people they talked in terms of stability. Some people they talk about statistical way. Some people in computer science they look in artificial intelligence way. But there are many articles, I didn't bother about that. Those who are interested in a particular of this can take up this. This is my advice to all of you. Okay. After this OD, first order OD, you have addressed the second order OD, and you know the second order OD. And second order OD, the linear form, if you take this form, it is linear. Otherwise, some other form, it will, other than this, will lead you a nonlinear equations, right? Okay. And in fact, the similarly, when for second order, this OD with linear form, you have this one, and first order OD, the existence uniqueness by Picard's successive method acceleration by Picard's method. Then you have this before Picard, you have Lipschitz, so that you know very well. Similarly, for second order, this OD also with initial conditions, the existence uniqueness is also well established, that you might have seen from the book. But if I look the boundary value problem, where the same second order differential equation with the two different boundary conditions. One boundary set condition is y of a equal to y naught, y of b is y1, that is y naught and y1 are constant, a, b are two different points, right? And so this is called the Dirichlet type, and then this one is called derivative type. Either you take this or this or this or this. This is four different types I have given, and the second one is this is a Neumann type because it is involves derivative or is called second kind. And then in OD, sometimes these are called the mixed kinds, where the where it is one is without derivative, one is with derivative, and is without derivative. And similarly, at the first point, it is with derivative, and second point with derivative. So one set you take it because you need two conditions at least to get to eliminate the arbitrary constant and to get a unique solution, provided if the IVP has a unique solution. But in case of BVP, with when two different points, because for IVP, these A and B are equal, that means A equal to B. But in BVP, when these are there, then, and in fact, where the life is sometimes simple if you have taken the homogeneous. But if you take the non-homogeneous VBP, here the VB is homogeneous. If fx is equal to 0, the right hand side is 0. This fx is 0. In addition to that, this y naught and yn is 0. So when it is homogeneous, the life is in the VB case little bit simple, but when it is non-homogeneous, then at least in the Storm-Liouville case, you might have done that. But I am not going to address on that because I want to show you some application and interesting things. This thing already I have told you, the Dirichlet type, Nobin type, and mixed type. Now, when in the IVP case, for first order as well as second order, the existence infiniteness is very nice way established. But in this boundary value problem, it do not behave very nicely as like the initial problem. Sorry, just a minute. Okay, so there are BVPs which solution do not exist, or or if a solution exists, there might be many more. Thus, existence uniqueness generally fails for the boundary value problems. So you can find out many examples. Actually, I will not show you example here, but I am giving a task to find out these possibilities of unique solution, no solution, many solution, and trivial solution. In fact, you will get in Google also. But Google is not always good. You create or see from book. Okay, okay, Sturm-Liouville problems you can see always where the Sturm-Liouville operator is this kind, where you will have this kind of equation with this kind of homogeneous conditions. Always you can get solutions where the solutions are called eigenfunctions because they are corresponds in the lambda. The lambda is called eigenvalue. But if you relate to the linear algebra, that's what you have seen, the linear algebra and differential equation related to each other. So, and when you compare with that, you will get here the lambda is called at the end. When you solve it, you will get its eigenvalue, and the corresponding solutions are called the eigenfunctions. So in the Sturm-Liouville case, you always get the series solution. That means the linear combination of many solutions. Okay. So the PD, the second order PD already well established. You have seen in the book the second order PD, which is in this form, and the classification, the seniors who are the MSc, BSc third year or MSc first year, second year, they know the classification very nice way is the elliptic and parabolic and hyperbolic according to the b square minus 4ac is 0 or greater than 0 or equal to 0. And in fact, the this last one is hyperbolic. The synchronization I little bit while speaking, I think I tell in different way, but this one is the hyperbolic actually. And you know the second order PD when it is more than two variables, this because this is for two variables, two independent variables x and y. So the classification is well established by this relation. But when you go for higher, more than two variables, then you can go with the matrix method and with this form, and then find the eigenvalues and then tell that if the eigenvalues is 0, then it is parabolic, and if they are the same, then it is and if it is all the eigenvalues non-zero and same sign, then it is called elliptic, because non-zero either positive or negative. So if all are positive, then it is, or all are negative, then it is elliptic. And when it's non-zero and have the same sign except the one of them, then it is called hyperbolic. I am not much to tell about this, but these are the few examples. The classical example which I always look is the Laplace equation, which is uxx plus uy plus in three-dimensional Laplace equation, and where the matrix is this, and you can see that all eigenvalues are positive. So if you look towards this are non-zero and the same sign, So that's what it is elliptic. And I'll show you today the application of Laplace equation, whether it is two-dimensional, three-dimensional, how in engineering application it has involving differential equation and numerical methods. And that's what you will see that the instead of OD, the boundary value problem, the PD, where the Laplace equation, and then you will see different conditions, basically the mixed condition, Dirichlet condition. I think I will not come with any time Dirichlet condition. I will come with the more than mixed conditions or the Neumann conditions. Okay, so the if you look my bullet points here, the mixed boundary value problem occur in natural way while modeling many problems of physics in particular, or in engineering in particular, in fluid mechanics. Okay, and while understanding application of such boundary value problem is of immense value to the physicists and engineers, but determining their solution analytically using most appropriate method or numerically by most appropriate method is the concern of applied mathematics. That's what we are interested to look, what is the suitable analytical or numerical method to solve a boundary value problem. As I told you in the outline of my talk, that I look on surface water waves applications, right? Now, why you need actually the study on surface water waves? My dear students, the wave has variety application, not only in fluid mechanics as well as in electrical engineering, like in sound waves, etc., in variety ways. Now, in particular, the water waves is important in the, as it has a wide range of application in coastal engineering, right? And here we look at the water waves, which are called the surface ocean waves, named as surface waves. Now, if you see that there are two kind of waves here, this wave is not that simple, but here is simple. So if you look this right one is the I'll name these as surface waves because this has the amplitude. It looks like the same in all cases. So I look such waves only. And how the surface waves is possible, you may tell that in ocean. Actually, if you look towards to a larger extent to the ocean, when the fisherman goes and then with the application, the in the contact with the boat, the surface waves are generated. And in fact, when there is no ocean in the natural, through the natural wind, the surface waves are also created. Now, these surface waves also propagates towards the shore, right? And when you have structure, whether it is offshore or near shore, you will have, you want to study and the study of application of surface waves with structures, which is having the application in engineering, basically ocean and naval architecture, right? Now let us start with a channel, or you look a channel. Suppose the channel is the upside, the upper side is free to the atmosphere, and this is the bottom of the channel, and the bottom channel is rigid, like you see a canal, and this water is coming from left to right, and along with the water there is a wave. Okay, so what you assumed, your physical problem is along with the water a wave is coming and propagating from left to right. Okay, and this I'll show you how, if you formulate it becomes it involves Laplace equation along with different conditions. Okay, so what we assume that when I want to state it mathematically, so I will look that I need certain assumptions, right? So the certain assumption is I will take the fluid, the water is here incompressible. Of course, there is no irrotational flow there, and the viscosity of the water is very small. So the if the is less viscous fluid is called inviscid fluid, then I can model it that the equation of continuity, which is given by this, somebody has learned the physics, then the equation of continuity is give rise to for the incompressible fluid, and then it gives rise to del dot q is equal to 0, this equation. So the equation of continuity, which is rho is the density and q is the velocity of the fluid particle, and then for this physics assumption incompressible fluid, the equation of continuity, the mathematical equation give rise to this del dot q, where this del is del by del x in del by del comma del by del y in coordinate form. You can write down for two-dimensional, and for irrotational motion, where I can write down q is equal to grad phi, and then once I substitute here q is equal to grad phi, this equation gives rise to the Laplace equation in two-dimensional. If you consider the three-dimensional, you'll get a three-dimensional equation. But let us talk about the two-dimensional flow rather a three-dimensional flow. Okay, so along the free surface, you will look also the equation of is called the Bernoulli's equation of motion, which came from the Euler's equation of motion. You do not know the details derivation, but don't bother about that. Let you assume that the Bernoulli's equation is give rise to this form, where it is simple equation where phi is the velocity potential. So in terms of q, I converted to phi in terms of here as it is given here, right? Where u is equal to the x component of the horizontal component of the fluid velocity, and that means the q is equal to u comma v, so that I can write that u is equal to del phi by del x and v is equal to del phi by del y. And that if you look here, that p is the pressure and g is the accelerated gravity, right? Now, so you got it this kind of equation where this phi is the velocity potential, and if you substitute del phi del x here, these are the square terms. So this is a nonlinear equation, but your differential equation is a linear one. That is the most beautiful thing, is that your differential equation is linear, whereas the boundary condition which you are looking, which you are talking on the free surface, in the free surface here, in the free surface, so if you look that, you are talking a equation which is already nonlinear, and y is equal to eta is the elevation. So this, if you took a full wave, I have not given full wave, so then you take this the elevation, right? This is called the elevation. Okay, so now if you want to make it this to the small amplitude, the linear theory, then this y equal to eta, then this term should be neglected, and this should be brought to 0, y equal to 0. Now that's what we neglected first. We want to linearize it because you want to solve the linearized problem. So you discarded it and then you wrote it. And I took in the pressure, which is the towards, because the free surface is open to the atmosphere. So the pressure, so at the free surface is the atmospheric pressure equal to with the pressure of the fluid. So that's what it should be. When they are equal, they should be equal to constant, but I took the constant equal to 0, so p equal to 0. So hence this term and this term there, and y equal to eta. Now, as I told you, the linear theory, it is the small amplitude of theory. So the elevation, the amplitude, the maximum elevation should be reduced to y equal to 0. That's what I have to expand this in terms of Taylor series. That's what the Taylor series has a big role, and you got this. Similarly, again on the free surface, the free surface is always intact with the fluid particle. That means it does not change as you move along the surface. So it doesn't change means dfi dt is 0. So f is y minus eta because the surface is this, and you substitute again, you'll get this. Now, if you look towards that, then again this is a nonlinear because it's elevation and this. Hence you discard this, so you got this and this. Y equal to eta. Again, you have to linearize it to y equal to 0 through the expansion of Taylor series expansion. So application Taylor series give rise to this one, 7. Now combination of 6 and 7. What is 6? This, because at the free surface you got this I equal to 0 as well as this one. So if you just eliminate the eta, you will get this one. Now on the bottom condition is the bed is flat, horizontal and rigid. No fluid can go inside the bottom. That's what is del phi by del 0 on y equal to h. So if you model this channel, which is you told that the water is coming from left to right, and then along with this, a wave is there, and then you got a Laplace equation in this region, and along the free surface, I talked a equation which is now you can see that it is derivative only, and then this is only Neumann type, and y equal to h. Now I want to solve this, but again I assume that if the fluid motion is simple harmonic in time, so I can write down the cos sigma t in terms sin sigma t. That's what I wrote it, e to the power minus I sigma t. Okay. Now if I substitute that the BVP for 8, 9, 10, the differential equation 8 with condition 9 and 10, it gives rise to very simple equation, again Laplace equation with this, and then the Laplace equation is this, and then the uh, this condition. Now you can see that by substitution it becomes the mixed condition, and again the Neumann condition is the 40, right? Now you want to solve this problem, which is the channel problem. I told you that the Laplace equation along with the, of course, if you take the viscous fluid, you will not get Laplace equation. You will get a complicated differential equation, and then you cannot solve the way I'm solving it. You cannot solve it. So the Laplace equation with this, you can solve it by variable separable method. You can see that you know the variable separable method in PD, and apply the variable separable Laplace equation, apply this condition, you will get this solution provided this dispersion relation is satisfied. This transcendental equation is satisfied, and this is called dispersion relation in water theory. You do not bother about that. Now this is a wave-like solution, because if I substitute e to the power I sigma t, which I have eliminated here. Now, if I put here e to the power I sigma t, it will satisfy the wave equation too. It's not satisfying only this one, because here is no t, so there is no problem. So it will still satisfy Laplace equation as well as the wave equation, because that's what its solution is, a wave-like solution. Okay. Now, and there are, because as you have shown, the Laplace equation for separation constant is greater than 0, equal to 0, and less than 0. So the equal to 0 case, you will not get anything. So the now less than 0 case, you get this solution, and greater than 0 case, this solution. So this is a non-wave like solution we told, because it won't satisfy the wave. So you may tell that, sir, why you consider both, because if you want to see that in water there is something like wave, but below the water surface inside there are some zigzag things. Like suppose I don't have here a transparent bottle. If you have a water bottle which is transparent, you just little bit shake, on the top surface you will see a wave, but below the surface some zigzag things which is vanishing quickly. These are called the non-wave like solution, right? So how you see that the mathematical solution, which is 15, is associated with a waveform, and the mathematical form 16, which is associated with the non-wave like form, right? Okay. Now, if I want to further analyze this solution, whether because in terms of propagation, then I am looking this transcendental equation, the root of this transcendental equation. And this transcendental equation, my dear students, you might have seen that to find out the roots of the transcendental equation, if you want to find out the root of the transcendental equation, always you might have done numerical analysis by the Newton-Raphson method. Now, my dear students, now before going for the Newton-Raphson method, and Newton-Raphson method requires the initial guess. And you always might have told, the teachers might have told you, or you might have seen in the book, that the initial guess always, if not given, you always get through the graph by plotting the graph. Now this equation, if I put that, if I put this, I'm sorry, where I put that. Okay. Now this equation, this transcendental equation 17, when I put it in this in this form, that k is equal to x by s tan hyperbole x. And now if you rewrite this again, so what I put, I substitute x is equal to, so that means I multiply h in both sides, that I k is equal to x by h, and then substitute back, I got it this. So ultimately this equation 17 I am writing in this form, where if I take this to left side and left to right, I got cot hypothesis equal to x by kh. So when I can write down this is m, where m is equal to 1 by kh, and k is sigma square by g. So I will take this as constant. H is the water depth, so I will take is constant. So, and you have seen that when a equation which is equal to fx equal to gx, in, you might have seen that when you want to have equation fx equal to gs, and you can plot then y equal to f of x, that means y equal to cot hyperbole x, and then plot also y equal to gx, which is y equal to mx, and the intersection point is the intersection points are the your roots of these transcendental equations. That's what. Now to plot that, what I did, that cot hyperbole x, to know the behavior, I wrote it to this one. And now this one, if you look towards this, as extend to infinity, it goes to 1, and when extend to 0, it is infinity, right? So that means 1 is extending to infinity, it is goes to 1. Okay, so it is when extend to infinity, this side it goes to 1, and then when extending to 0, it is goes to infinity, and extend to 0 is this, and the infinity goes to infinity, right? Now come to the other one, again cot hyperbole x, I can rewrite this form, and I will tell that this little bit about extend to minus infinity, it goes to -1, and when it's 0 minus, it is go to minus infinity, right? So this is the curve. So one curve is this, another curve is this, due to this cot hyperbole x. Okay. Now the asymptotic analysis, then another was y equal to mx. So y equal to mx is I draw this one. Okay. Now the intersection point, one is this, another is this only. There are the several points are given, but don't bother about that. The intersection point, this one and this one, that means two roots. So this time, so for k is equal, this is the actual plot from MATLAB when k is equal to 1. So, and you have seen that there are two real roots. One is here x naught, another is minus x naught. So whatever roots you get, negative of that is also is root. You can test that. If k is a root, then minus k is also root. Okay, so you may ask that, is there any other roots of this transcendental equation? The answer is yes. How do you know that? Now let us again analyze through a different way, through graphs. Okay, and if you look towards this, I can tell you that this transcendental equation, which is in this form, if I put k is equal to I gamma, and then I can get this k h into, instead of hyperbolic, I get x tan x equal to 0. So earlier it was cot hyperbolic x, but it is cot x now, and here it was positive, now it is negative of x by k. So cot x is equal to minus mx. In the previous case, it was cot hyperbolic is equal to plus mx. So only this substitution k is equal to I gamma, I got it this one. So instead of gamma, I'm writing x, so that at least you can solve the equation easily. So now cot x behavior at cos x by sin x, when x is equal to n pi, I can tell that it is infinity, and when it is at these points, it is always 0, because the cos where 0, it is 0, right? Okay, so with this behavior, we can tell that these curves are there. Okay, the asymptote, these are the curves. Now y is equal to minus mx is, this is the curve. Now the intersection point is this, and this side also it will go this side. So there are infinite, because it expands in both sides, is infinite number of roots are there. Okay. So the infinite number of roots. So what we claim that the transcendental equation, this equation has two real roots. One is k naught, another is minus k naught, and there are infinite number of purely imaginary roots in the form of I gamma n, right? So this equation has real roots. That mean, in fact, this equation came from this equation. So this equation has infinite number of imaginary roots, which is the form of minus I gamma n. Okay, that is the very beautiful. Now that means it looks like that the channel problem which you came across, that a Laplace equation with two boundary condition, where the solution is this e to the power ikx into some function of this f of y, which is this one, where the k is satisfied this transcendental equation, which has two real roots and many imaginary roots. So if you write full solution, this plus infinite sum of this, right? Because you got the linear combination of all solution is the superposition principle tells that all linear combination is the solution. Okay, so this is the mathematical way. I think I have 10 minutes. I'll tell you some application, but some other time I'll tell you method of solution. Now you have seen that how variable separable method along with a numerical, the Newton-Raphson method gives you the idea about the solution to a channel, simple channel, where it is just waves traveling along the water. Now the breakwater, you have seen that the surface waves are means the waves are coming, right? You can see that the surface waves and is hitting to the this real estate belt, or you can tell that this belt, this area, and that's what this is there to protect these houses and the real estate, right? Now this is another kind of breakwaters. You can see this kind of things where if you have visited TFR Mumbai, near the TFR Mumbai, thus in the sea beach, big stones are there, which are called also breakwaters. These are the different breakwaters taken from this. This is another kind of breakwater to where to protect these floating objects. This is another kind of breakwaters to protect the seashore. Now, applications of such breakwaters is to protect the BLFS, where is man-made islands. Now, these man-made islands are already identified in Japan, in China, in Taiwan, and in Australia, in different places actually. And because in Japan already they have a floating airport, and this floating airport first was it is very interesting, and there are many floating storage facilities in Singapore and other places as well. There the this waves comes and strike this one. So the sustainability of these very large floating structures is of importance. So the people study mathematically that the force exerted by this structure. So if you want to study numerically or the through mathematical numerical modeling or mathematical modeling, you need to understand what is the basic differential equation and the boundary condition, so that you can through the equation, you can get the solution and hence the force, right? So this is the BLFS, as I told you, the floating storage, and this is another floating bridge you have seen. Of course, these are offshore structures which are required actually to recover the oil and gases. And this is another floating objects. This was at part of this Tokyo at Japan. Is the similar types actually. And so now this breakwater are required, or the BLFS, the floating structure, if they are the thin barriers if I tell that suppose a barrier or a plate which is very thin, it may be vertical or horizontal. So if I take that and waves comes and strike, then some part are reflected back and transmitted over this. Then suppose in the same fluid is there, but I'll consider a object which is very thin. So let add this y. Instead of y is vertically upward, I took downward. Doesn't matter. The coordinate axis is according to your convenience. You can choose also, no problem. And when I took and I placed a barrier of up to distance a from the free surface. So this is the free surface. There are waters here and wave is traveling and striking the barrier, and some part of the waves are reflecting back and some part of the waves transmitted. I couldn't bring here there are actually films which have been produced for this the lab in Kharagpur, in Madras and some other places. But I am sorry that I couldn't keep. Otherwise, I have to show a PPT file rather a PDF. Okay. So now if you want to model again this equation, if you take the same assumption what you did in channel flow, and then you will have Laplace equation, and then free surface condition is same, bottom condition is same. In addition to that, you will have on the barrier, in this barrier, you will have the this because it's a vertical barrier, so horizontal component of the velocity is 0. So del phi del x is 0. And in the suppose if you take two region, if you want to solve the problem between two region, one is x less than 0 and is x greater than 0, then you will get the in this gap the pressure is continuous and the velocity is continuous, that you must apply. And along the far field, then you will have this condition where this r is the reflection coefficient with reflected wave, and is the transmission coefficient associated with the transmitted wave. Okay. Now the incident wave, if there is no barrier, then the wave simple coming and traveling without any hindrance, that can be considered as the incident wave, whose solution I just show you few minutes before, which is of this form, provided this first transcendental equation is satisfied. Now question is how to solve this BBP to get R and T phi. Now can I only apply the separation variables method and can get it? The answer is that up to certain extent, and because you will apply only this condition, these two conditions. If you apply with variable separable, you will get up to some extent the series solution. So the all solution combined is called series solution, which are one is x less than 0 is this one, and is x greater than 0 this. Now if these two solution is a solution on the whole boundary value problem, it has to satisfy the condition on this barrier, condition on the gap, and this of course this far field condition I have taken care here. Now the rest condition I have to apply. So when I apply a rest conditions, I get a system of equations. I'll not show the details. If some other talks, I'll give the details. Now if I get a system of equations and in the form of x equal to b, and you know that if a system equation I get, I can solve by just simply using Euler's method or whatever method you like. And in fact, I used the least square method. Why I used it can be solved by algebraic least square or analytical square, but details I am omitting because time is short. And in case you are interested, I'll talk to you later. And in fact, when I consider this algebraic least square methods, this equation and this this equation, I can just tell you that one is this equation, and this is L bar, this is L bar, another with L. Yeah. So one is with the barrier, another is the gap. So I have to choose different y points to get different equation. So that's what I have chosen. You can see that equal discretized points. So to get the numerical solution, because you have to solve numerical through computer. So that's what I have chosen, how many points, etc. I have taken equal scale points, and then if you are taking unequal points, these are the Chebyshev polynomial of first kind. I also have tested that Chebyshev polynomial. Second kind, you can see that these are the, again, one has to struggle and read more things to apply and to see that how you are getting solutions. So the solutions is numerically, which is obtained by solving the reflection coefficient, transmission coefficient. This is the just the numerical, some numerical values. Okay. And this is if some other time we will see that how integral equation has the classical freedom integral equation second kind has also role, and how it is required also to fluid mechanics problem, and we can discuss later. So these are the few things actually which I highlighted, and I only told you the linear problem. The non-linear problems are not so simple. So in conclusion, I started with the COVID problem, IVP and its importance. Then I talked about the BVP, but I didn't tell you the BVP for OD and how the equation no solution, etc. You will find out. And in terms of applications, I told you the scattering of surface waves, where you will see the application of numerical methods, whereas numerical analysis, etc. are required, right? Okay, so this is the two papers. This is the paper where the second problem was highlighted, and these are my students. I think this first two, Sikumar, Arun already graduated. This Sophia and Amandeep's also already graduated during the COVID. Navin is in the 5th year now or 6th year, and these are the current students are still with me. And for you people, the students of this St.Ann college, for that you should have small projects and try to do the coding to MATLAB very easy, or Skylab you can get freely from the internet. The software Skylab is also freely available. In case MATLAB sometimes if your institute doesn't have, but if do not get, go with Skylab. The same way you can write down. And I can tell you, I do not know the always MSc students can apply variety internships. You have, I think just recently NASA internship time is over. Always the time comes in November and they give by March the result. And in vacation, summer vacation, you can do wherever you like. But at least those who are in BSc and in you can, some of you students can apply the MTTS. The advertise came, I think, just few days before, and the applications, online application starts from 10th January. So you just go to MTTS this time, IIT Mandi, IIT ISM Dhanbad, and IIT Madras. These three places are doing, and you apply. The top students, at least 2 to 3 can or 4 can go these places and always can get a chance to interact with the people in MTTS. And if you do not have these students clubs, you can start some discussion like a seminar presentation at least among MSc students, or so at least the skill they will start among discussion among themselves. So this is from my side for you people, and that's all. This is the main gate. If you are coming to Delhi sometimes, so visit Punjab, and then from Chandigarh, my institute is just 45 kilometers away from the airport. You can get a chance to visit me as well. Thank you very much listening my talk, and thank you again, madam, for inviting me to this talk. Special thanks to Santoshi ma'am and Javier ma'am. Thank you.
Thank you, sir.
Any questions? I'll be happy to answer.
Thank you so much, sir. Though you are not keeping well, but still you have accepted our invitation.
Yeah. Actually, I am not still well, but what to do?
Yeah. Really, we are thankful to you, sir. Sir, I have one query. Can I ask you?
Yeah.
Sir, when we, deal with highly nonlinear boundary value problems,
Yes, sir.
when we are, going for the governing equations. So there, for the same governing equation, is there any chance of, we changing the boundary values? Like suppose if we have, done a problem with existing boundary values.
Is involving ODs or PDs you are talking?
Involving ODs, sir.
Okay, boundary value problem with the OD only. Okay.
Yes, yes, sir. So can we change the existing boundary values to new boundary value on the same problem?
No, you can change. Suppose if you change, suppose the existing uniqueness will, suppose you know that the problem has a solution. Okay.
Oh,
Suppose if problem has problem has a solution, then if you just change, suppose if I have 1 point is 1 and 2, right?
yes, yes, sir.
Now I am look what we do in finite difference method. We look in between points the values, right? Because at the end points it is known, or suppose in a rectangular domain it is known, and you are looking inside some other points, what is the values, right?
Yes, yes,
So now you tell that, suppose if I am not given at 4 corner points, but I have given in 4 in between points, so I can get nearby points the solution then, right? That's what the approximation.
yes, yes, sir.
So that will not give any more change actually there.
Okay,
Okay.
okay.
So you will get nearby because we are looking at approximate solution only.
Yes,
So
yes.
so there will be no problem there.
So for the solution that we have obtained, even if we change the boundary conditions, it may not be of that much use.
Actually, it's suppose if you consider a natural problems, right? Suppose it's a problem which is associated with nature,
Yes, yes, sir.
it has a meaning, right?
Yeah.
You have to look that what kind of problem you are looking with the boundaries.
Okay.
Okay, so what we look in the actually in more basically what we look in the realistic only, because in when we tell in classrooms, we only take very on the boundary only, right? We take our 2 different points if it is just woody case, right?
Yes, yes.
But in PD case, suppose like a Dirichlet problem, you look for a rectangle. So rectangular we consider sometimes 1, 0, then 0, 1 like that, right? So very simple one we take.
Yes,
And
yes.
in that simple one, suppose instead of 1, 0, and 0, 1, if you take up to 2 instead of 1, 0 to 2, and 0 to 2, again 2 to 0, right? So one point is 0, 0, another point is 0, 2, another is 2, 0, then 2, 2. So that means you are extending from 1, the rectangular where 0, 1, 1, 1, 2, up to 2.
Yes.
So that's is you are getting enlarging your domain only. That's all.
Okay.
Right. So
Yes.
so you should look that actually what is your domain and what is the domain you are discussing. If it is a physical problem which has a meaningful, the domain is remain same, right?
Yes.
The domain you cannot change it, and in that domain, like in for my case, the domain is minus to infinity to plus infinity, and the y part the is 0 to h. The h is the depth actually. If I take 10 meters, that is 0 to 10 only.
Yes.
If I take 100, then 0 to 100, that's y only. So my domain is fixed then, and in that domain, what I look different behavior of the wave phenomena, right? I am not changing the domain. I am changing the boundary only. The boundary I'll take sometimes instead of flat, I'll take a little bit curved one. I'll take a triangular one. Suppose if I take a triangular boundary, I'll get a different solution.
Yeah.
The curve, if you plot it, the solution curve will be different when you take the boundary as a concave boundary. If you take a convex boundary, you'll get a little bit a changeable solution also, right? So the solution naturally depends on your boundary, right? So it is depend upon what kind of boundary you are taking. Suppose if it is simple, suppose like as I told you, 0, if you are talking in the flat bed, y equal to h. If I take 10 and if I increase some 10 to 15, I will not get more changes there, right?
Yeah, yeah.
But if I change y equal to 15 to y is equal to hx is a sin x or sin y, y is equal to a sin or sin delta x or something, then naturally my solution will change.
Yeah.
You got it?
Yes, I got it.
Yeah.
Thank you so much.
Any more questions from the students?
Sir, next year we are planning to introduce projects for the final year students in the last semester.
Okay.
What type of projects should we give? Yeah, for
MSc, MSc,
no. For undergraduate students in the last semester. And one more thing, can we give one problem to 5 students, or each one should be given a problem for the project work?
It's that sixth semester course you are telling, huh? On the
Yeah.
sixth semester.
Yes.
Sixth semester, you want to introduce a project.
Yeah.
It is depending upon the level of the student as well as how your teachers are involved with the student actually.
Mhm.
See, we are also what we did in our MSc students, I'm telling you. Initially, we had project is compulsory. Then we told that those who are not doing well, let them not do the project. Then after the student told that, sir, even the project is simple. I should take in terms of project because project means it is not to learn the knowledge from the subject. The project involves the document, how you are present, how you are writing the document, like in terms of starting from title, abstract, and then it has a content style, right? Up to reference, and in between the contents chapter wise or section wise. So it usually make that one thing is the document. Another thing is that the knowledge, how much he or she gained and already put in the document. And the third thing is when he or she presents, what is the level, and they will learn that okay, this is the small project, whether it is already given in the book, but still they studied, and in addition to the book, but little bit more way they have fascinated way they learn the PPT and got it. So this takes time also. So students learn at least some extent whatever the project you decide, whether it is from the book which you have not studied, or you give in a new topic like I gave you COVID and they will search and get it. So it is possible always. And coming to that, your second part, whether one student do or five students do is depending upon your problem. If the problem for them, suppose they are the sixth semester student and they have already different courses, how many courses is there and how much time they can give to this project, depending upon that you decide that okay, if it is a difficult we should give this level or the just simply easy one. Like suppose if I tell okay, you got the history of pi, so just you'll search many things and 10 pages of pi information you'll bring and will tell us, right? So it's depending upon the strength of the project, what you are giving to the students.
Okay, sir. Okay, sir.
I'm sorry.
Sir, then can
Yeah.
we give them projects on something like history of pi?
Yeah, it is just I'm giving example, but
Because-
it's not always good to give
Yeah,
the
because that is a very basic level, where
basic. So
yeah,
just I gave an example, but it
example.
is not necessarily should be just history.
So,
Always you put something they should solve, and because mathematics, right?
yes,
So
yes.
like I told you that if I give you the simple system of nonlinear equations with conditions, one has to solve by Euler method or Arche method, right? So
Yes.
in the book, maybe one simple toy problem is there. Now, one has to spend, one has to get from the like from the research paper, what is the COVID problem nonlinear equation, and can you get solve the same whatever is there, let them solve by MATLAB. But for BSc little bit maybe tougher, but MSc student can do it. But your program is still up to BSc or MSc is there?
BSc, sir.
BSc, sir.
But
Yeah.
still, I think some is this problem up to your means what you covered actually in theory. Based on that, it is possible. Based on that,
Oh, okay, sir. Okay.
so
Thank you.
you look that what you are teaching with respect to that, some extraction is always possible. See, if you look one book which you are teaching, suppose I teach numerical method by John Anger Jain book. There is another book where these days like sometimes this if you are teaching, suppose one is numerical methods, another is optimization, this that now there are books I think, but though I am not following, there is a mathematical modeling books also available where some simple problems of this optimization is there, this numerical methods are there, and differential equation, there are a lot of things are there. Okay, so once you make it one set, the similarly, so every year they can change and they can look it.
Okay.
Thank you, sir.
On behalf of the Department of Mathematics, I take this opportunity in expressing my sincere gratitude to Dr. Subhash Martha, Associate Dean Students, IIT Ropar, in being generous enough in accepting our invitation and gracing the occasion by sharing his knowledge and expertise with us. Thank you, sir, for the valuable research ideas and applications of differential equations, numerical methods like the linear differential equations with initial conditions to find the people affected with coronavirus, Laplace equations with boundary conditions, boundary value problems, and study of applications of surface waves, which we have learned through your session today. We look forward to more such fruitful sessions from you in near future. Thank you very much, sir, for accepting our invitation and gracing the occasion today. Thank you, participants. I request all of you to please switch on your videos for a quick photograph.
Just a minute, my video is still not working, I guess.
Oh, try.
Just a minute, let me switch.
Students, you can switch on your videos.
Only Santoshi picture is same. Speaker is not to be seen. Navya?
Ma'am, I think there's some problem with sir's video. All the girls have switched on the video.
How it is looking big, no? Your picture like that. Speaker picture should be there. What should we?
Ma'am, I can view only your picture.
For everyone, it is seen like that only, no?
Yes, ma'am.
Yes, ma'am. Yeah. Now I can see Navya.
Now, yes, Navya.
Maybe some problem with sir's end, ma'am. He's not able to switch on his video. Or
Students, please switch on your videos.
yeah, few girls have switched on, Navya. Few, not all. Few have switched on.
Yeah, ma'am.
Sir's video is not working.
Yeah, I think it works.
Now you take.
Yeah.
Have you taken, Navya?
Yes, ma'am. I took, ma'am.
Sirs, you have taken. Thank you, sir.
Thank you very much. Actually, I am not so well, but still, I do not know how I managed to what it is.
No, sir. It was very nice, your lecture. Thank you so much, sir. Thank you so much.
I all are good speakers, even Tapas as well as I have seen your poster that you got 4 speakers from Ropar. Very nice. So, and if I could know that Jitendra and Tapas and Saira are giving, I could have denied you actually. Okay. Thank you.
Okay, sir.
Yeah. See you then sometimes.
Thank you. Thank you so much, sir.
Thank you.
Okay, bye everyone. Bye.
Bye, ma'am.
Thank you, ma'am. Bye, ma'am.
Can you provide the feedback link to students, Nabu?
Okay, ma'am.
Just share the feedback link so that they will fill it. Students, please fill the feedback link. Girls, I request all of you to please fill the feedback form and then leave.
Ma'am, feedback link is shared.
Okay. Well, feedback link ma'am has shared. I request all of you to please fill it and then leave the meeting. Navya, should I close the meeting, end the meeting for everyone, or we'll wait for 2 more minutes?
We'll wait for a few more minutes, ma'am. Let them fill the.
Okay.
Ma'am, only 13 students are there.
Yeah,
I think we
that's
can.
13 means, yeah, along with 3-4 of us, maybe there are
Yes.
7-8.
Ma'am, I think we can end the meeting.
What, ma'am? We can leave, huh?
We can.
Okay, I'll end